In this lecture, I am going to discuss an example problem for covariance. The problem is the pair of random variables x and y takes the values 1, 0, 0, 1, minus 1, 0 and 0, minus 1, each with the probability 1/4. Now we need to find the covariance. Now first let me plot this joint PMF. First of all, there's a joint PMF. So I have x-axis, y-axis, then the points are, let's say this is 1, 0, and this is going to be 0, 1, and this is going to be 0, minus 1, and this is minus 1, 0. So there are 4 points, and each points take the probability 1/4. Okay, now we need to find the covariance. So the covariance formula equal to, the short form is E of xy minus, this is not covariance, this is a correlation coefficient. So covariance of x and y. Okay, so E of x times E of y. So this is a formula. Now we need to find out what is E of xy, E of x and E of y. Now we can find these values by looking at the figure. Conceptually we can find out, or you can work out mathematically, and you can find the covariance of x and y. Okay, let us first find the values conceptually by looking at the probability mass function of x and y. They are symmetric around 0 point. See, it is symmetric between 0 and y, and similarly 0, minus 1 to plus 1, and here this is symmetric between minus 1 to plus 1. So by looking at this figure, you can see the center of gravity or the center point of your probability mass function equal to 0, and similarly E of y also equal to 0. Expected value of y is also 0. Okay, and now E of xy, if you want to calculate, by definition you know that x times, it's a discrete, so I need to use summation sigma xy times the joint probability mass function of P of xy. Now when x takes a non-zero value, y takes a 0 value. Look at the points. Either you have 0, 1 or 1, 0, 0, minus 1 or minus 1, 0. So when x is 0, y is non-zero. When x is non-zero, y is 0. Therefore, it takes complementary value. Okay. Therefore, this E of xy is 0 for all possible values of x and y. Therefore, we can say that E of xy equal to 0. So therefore, covariance of x and y equal to 0. Okay. But when I say x and y equal to 0, that means what? X and y are uncorrelated. Okay, that means E of x and y, covariance of x and y equal to 0. But however, x and y are not independent. X and y are not independent. Y is not independent, that means what? X and y are dependent, right? How do we say that x and y are dependent? Because a non-zero value of x fixes the value of y to 0. When x is non-zero, then y is 0. Similarly, when y is non-zero, then x is 0. Therefore, when I come to know x is non-zero, then I can tell you what is the value of y is going to be. Y is going to be 0. Similarly, when y is not equal to 0, that is non-zero, then I can tell you automatically that x is 0. Therefore, x and y are dependent random variable. Okay, x and y are dependent. Even though x and y are dependent, your covariance is going to be 0. Okay, in this particular case. Therefore, we cannot say that if covariance is 0, that implies that the random variables are independent. As we have seen that if x and y are independent, then we can say that covariance of x and y equal to 0. But the converse is not true, right? Even though the x and y are dependent, then your covariance is going to be 0. That's what we are trying to prove in this or understand from this example. Now this I derived through conceptually. Now let us discuss through conceptual through mathematically. So I have 4 points. The points are 0, 1, then 0, minus 1, 1, 0, then minus 1, 0. These are the 4 points. Now we need to find 4 quantities: expected value of x, then expected value of y, then expected value of 3 quantities, e of x, y. So first let us to find out e of x. In order to find out the expected value of x, I need to find out the marginal probability mass function px of x, and to find the expected value of y, I need to know py of y. And here straight away I can use the expected value, the probability mass function of x and y. Okay. Now let us find the probability mass function of px of x. So this is going to be summation over summation over y summation over y p of x comma y. Now if you look at the given probability mass functions, where x takes the value of -1, 0 and 1, y also takes the value -1, 0 and 1. Now therefore y is equal to -1, 0, 1. These are the 3 values it is going to take. Now sum over y over this values. So pxy of -1, x -1 plus pxy of x 0 plus pxy of x 1. Okay, so this is my px of x. Now substitute x equal to 0, x equal to 1, and so on and so forth. X equal to -1, let me put -1. So px of -1 equal to pxy of -1, -1 plus pxy of -1, 0 plus pxy of -1, 1. Now -1, 1, this is 0. We don't have any points like that. Then -1, y, -1, 0, the probability is 1/4, plus -1, is it -1, 1? No, this is 1 actually. This is 1. Okay, I'm sorry. No, this also 1. So then this is +1. This is +1. Let me write properly. This is -1. Then one minute, let me rewrite. This is, I have done something mistake here. This is correct because here -1, 0 and -1. Now put x equal to -1. Then this is pxy of -1, -1, pxy of -1, 0 plus pxy of -1 +1, and this is +1. Okay, it takes -1, 0 and -1 y +1. So therefore this is +1, correct. So this is going to be, this value is 0 and this value is 1/4, and this takes the value of 0, therefore 1/4. This is therefore px of -1 equal to 1/4. Now substitute x equal to 0 in the above expression. Then pxy of 0, -1 plus pxy of 0 comma 0 plus pxy of 0 comma 1. So this is going to be 1/4, and this one is 0 and this one is 1/4, so this is going to be 2/4 when x equal to 0. Therefore the px of 0 equal to 1/4. Similarly you can find out px of 1. This also is going to be 1/4. I'm not doing the calculation, so if you do that you'll get 1/4. Now if you draw the PMF of this, then when x equal to 0 it is 2/4, when x equal to 1 it is 1/4, when x equal to -1 it is 1/4. So now if you, this is the probability mass function of x, that is marginal probability mass function px of x. Now if you calculate E of x, then this is equal to 0. You can simply substitute the formula and you can say, or looking at the probability mass function itself, you can identify, okay, center of gravity of the probability mass function, that is summation over x px of x. Now this is when x equal to -1 the probability is 1/4, when x equal to 0 the probability is 2/4, then when x equal to 1 the probability is 1/4. So anyway this is 0, and this is -1/4 plus 1/4, it is equal to 0. Therefore the expected value of the random variable x is 0. Similarly the same type of calculation you can do for E of y also. So finally you will end up with the E of y equal to 0. Now let us find out E of xy. E of xy equal to sigma xy pxy of x comma y. Actually this is double summation, so let me write out two summations here, where let's say y takes the value -1 comma 0 comma 1 and x takes the value -1 comma 0 comma 1, and here xy times pxy of x comma y. Now let me expand with the inner summation. So this is going to be summation over x equal to -1 comma 0 comma 1, and here then when y equal to -1 you'll get -x pxy of x comma -1, plus when x equal to 0 it is anyway 0, sorry, y equal to 0 it is 0, 0 times anything 0. When y equal to 1 you'll get x times pxy of x comma 1, right? So this expansion. Now substitute x value, different values. Let me substitute x equal to -1 first. -1 times p of -1 comma -1, this is xy, plus this x equal to -1, so -1 times pxy of -1 comma +1, right? Then when x equal to 0, then 0 plus 0. When x equal to 1, then 1 times pxy of 1 comma -1, then 1 times pxy of 1 comma 1. Now if you look at the probability of different combinations, then this guy equal to 0, -1 comma 1, there is no probability, and here also this is going to be 0, and this also going to be 0, and this also going to be 0. So finally the expected value of xy equal to 0. Therefore the covariance function of x and y is equal to 0. But the random variable is not independent. We know that when two random variables are independent, then we can say that the two random variables, the covariation between the two random variable is 0. But here the random variable is not independent, even though you are getting covariance equal to 0. So this kind of cases sometimes occurs. So you cannot say that when the covariance is 0, then the random variables are independent. Okay, so whenever the random variables are independent, definitely the covariance is equal to 0, but the converse is not true. That means when covariance is 0, then you cannot claim that, or you cannot say that those two random variables are independent. Here the random variables are dependent in this particular example. Okay, so this result we can generalize. Okay, in particular let us assume that x and y satisfy the condition, that is expected value of x given y is equal to small y is e of x for all y. Okay, so when y is given, then I can say what is x. Okay, so that's why it has come like this. So then assuming x and y are discrete, okay, then total expectation theorem implies that like e of xy is equal to summation over y times py of y times expected value of x given y is equal to small y. Now this we know that it is e of x. Now substitute e of x in this, sum over y times py of y times e of x. Now since e of x is a number, okay, so you can pull out of the summation, and sigma, this is sigma over y times the marginal PMF of y, and this is going to be by definition e of y. Therefore it is going to be e of x times e of y. This is expected value of e of x and times e of y. Therefore whenever you have a this kind of a result, then covariance of x and y is equal to e of xy minus e of x times e of y, which is e of xy equal to e of y minus e of x times y. So this is 0. Okay, so x and y are uncorrelated. The argument for the continuous case is similar. The same kind of argument you can extend for the continuous time random variable also. So the final point is x and y are uncorrelated if covariance of x and y equal to 0. That means that it is not necessary that x and y are not independent. Okay, so a non-zero value of x fixes the value of y to 0 in this particular example. So the final remark I would like to mention here, if x and y are independent, e of xy equal to e of x times e of y, which implies that covariance of x and y equal to 0. Thus x and y are independent, then they are uncorrelated. However, the converse is generally not true. That means what? If two random variables are uncorrelated, then you cannot say that x and y are independent. Okay, that is if x and y are uncorrelated, does not imply then one cannot say that x and y are independent. That's it. So there are some properties for covariance. Let me record here. Okay, a few properties of covariances, and these properties are easily derived from the definition of the covariance. So let's say x and y are two random variables, or okay, let me take one more random variable, c. X and y, x, y and z are any random variable. That means what? Any in the sense here it can be continuous random variable or discrete random variable. And then a and b are scalars. There are two scalars. Now you can use this. I think I have already proved this. Covariance of x with x itself is variance of x. This is one property. And the second one is covariance of x comma ay plus b is equal to a times covariance of x comma y, or I can say covariance of ax plus b times comma y equal to a times covariance of x and y. Then linear combination covariance of sum of two random variables x and y plus z is equal to covariance of x comma y plus covariance of x comma z. So these are some properties that you can prove on your own. Okay, so let me stop at this point. Thank you very much.